Okay, problem 17-6. The hemisphere is formed by rotating the shaded area, so this shaded area, around the y-axis. Determine the moment of inertia IY, about the y-axis. Express the result of the terms of the total mass of the hemisphere, and the material has a constant density rho. So we're going to solve the equation I equals rho integral r squared dv. Because rho is constant, we can leave it outside the integral. Now r is going to be the distance from the y-axis. Okay, and we'll do it in the x direction. So I'm going to draw a dv, which will be cylindrical in shape, because I want a constant x. So if I have this cylinder here, if you can think of it, it's a little dx right there, and it goes the full height and it rotates around y, creating a cylindrical shell. And so as that varies from 0, a little tiny cylinder here, to x equals r, a wide, short cylinder there, it will encompass the whole volume of the hemisphere. So we have a little dx. So dv is going to be the height here, y, times the surface area of the end. And the end of a cylinder, so the end looks like this. So the end, we're going to do 2 pi r, which is the circumference, times the thickness dx. Now r, instead of r, really we want x, because it's the distance from the y out. So r is actually x. So we can do y 2 pi, let's rewrite that, 2y pi x dx. We don't want y, we want x. So rewriting this equation in terms of y, we will get y squared equals r squared minus x squared. So y equals the square root of r squared minus x squared. So dv is actually 2 pi x square root r squared minus x squared dx. So there's our dv. Now look at this. This r squared is not that r squared. That r squared is the distance from the y-axis. So this r squared is actually x squared. So writing the equation now, we have the integral of x squared, which is that r squared, dv, which is all this, 2 pi x square root r squared minus x squared dx. Now at this point, we need to do a substitution. So I'm going to call the variable k. And k equals r squared minus x squared. If k equals r squared minus x squared, dk equals negative 2x dx. So rewriting the equation, I equals, we'll bring pi out as a constant. So rho pi integral x squared, and that is going to be right here. So x squared is k, swap those two, r squared minus k. So we'll put r squared minus k for x squared. Now 2x dx, 2x dx is negative dk actually. So I'm going to put a negative out here, and I'll replace the 2x dx with dk. Put it on the end. And then This is the is k to the 1/2 power. Okay. Now let's multiply the k through. So now I is equal to negative rho pi integral r squared k to the 1/2 minus k to the 3/2 dk. Now we integrate. R squared, it's a constant, and k to the 1/2 becomes k to the 3/2, and then we divide by 3/2, so we could flip it upside down and make it 2/3. K here becomes 5/2, divide by 5/2, flipping it upside down, 2/5. Now, we don't want k, so let's replace k with r squared minus x squared. So negative rho pi 2/3 r squared minus x squared 2/3 minus 2/5 r squared minus x squared 5/2. This should be 3/2 right here. Now we want to integrate this from x equals 0 to x equals r. Now if we're integrating from r, so if we put in r, we get r squared minus r squared is 0. And we get r squared minus r squared is 0. So putting in r results in 0. Now we want to put in 0. Now if we put in 0, we get r squared and r squared, the x squared goes away. But we want to subtract that off, so that will cancel out the negative sign here, and it'll become positive. So rho pi 2/3, if we put in a 0 here, now we have r squared to the 3/2 becomes r to the 3rd, minus 2/5, that's 0, that becomes r to the 5th. So now we have 2/3 r to the 5th minus 2/5 r to the 5th. And so that's going to be 10/15 minus 6/15 is 4/15 rho pi r to the 5th.